is the Kwinana grain terminal, one of the largest storage and shiploading facilities of its kind in the world. It's located on Australia's western seaboard, just south of the city of Perth, and it's been commissioned by the farmer-owned Cooperative Bulk Handling Company Limited of Western Australia. The structures: massive vertical silos now under construction, and the completed horizontal storage facilities. The combined units capable of holding 32 million bushels of grain. Project value, about 50 million Australian dollars. What you can see here at this early stage of construction is spectacular enough, but below ground, a major engineering feat has already been accomplished. This is a project where the huge size of the structures, combined with the poor ground conditions, created unique foundation problems. The foundation contractor, Frankie Pyle, Australia. The terminal, designed by the consulting engineers McDonald, Wagner and Priddle, fronts onto Coburn Sound. The complex comprises a shipping gallery capable of handling bulk carriers of up to 100,000 tons. Wheat is fed by way of underground tunnels from a storage complex comprising the existing number 1 horizontal storage shed, to which is being added an additional horizontal shed to the north, and a vertical silo complex of 144 cells and a working house on the seaward side. The site is located in a belt of wind and marine deposited sands. The soils engineering firm of Ground Test Proprietary Limited were commissioned by the consulting engineers to carry out a detailed investigation and analysis of the subsoils. A total of 60 test bores were installed to depths of 27 to 45 meters. The drillings revealed up to 25 meters of loose sand overlying a 3-meter band of soft clay. Beneath the clay, decomposed limestone, improving with depth. The groundwater table 3 meters below the surface. The vertical silo block and working house, a massive structure equivalent in height to a 22-story building. The 144 silo cells with a total working weight of some 600,000 tons to be supported on a raft imposing a ground-bearing pressure of 300 kilopascals. This creates high stress intensities in both the sand and the clay layers. The loose in situ sand and the compressible clay layer would be incapable of supporting the structure without intolerable differential settlements. The cost of the conventional foundation system incorporating piles to some 43 meters in depth was prohibitive. The solution adopted by the designers was unique. It called for the improvement of the unstable sand layer to a specified density through its entire depth of 25 meters. At the same time, the groundwater table was to be lowered over the whole area to produce pre-consolidation of the clay layer and to permit underground construction in the dry to depths of 16 meters. Now, whilst this solution offered a considerable saving in both time and cost, it presented a formidable construction challenge. Competitive tenders specifying performance were called for. Firstly, the compaction of 1.5 million tons of sand in situ to a depth of 25 meters, not previously attempted on such a scale anywhere in the world. The onus on the contractor to determine the work and method necessary to achieve the specified density. Secondly, the lowering of the groundwater to 20 meters over a vast area of 10 hectares, this involving the removal of a gigantic quantity of water and the continuing battle to maintain a dry site. Again, with the onus on the contractor to design, install and operate a suitable dewatering system. All this to a rigid time schedule. A formidable challenge indeed. Project manager John Blewett.
Frankie Pyle won the contract for the foundation works. We handle the dewatering element in association with Stan Australia. The dewatering system can be seen here on the plan. 30 high-capacity deep turbine wells were installed on the north end and the south end of the site in the area of the silos. These wells rapidly removed the bulk of the water in the upper layers. Combined with the wells, 2 lines of eductors were installed on the western boundary and on the eastern boundary to advance the drawdown in the lower levels. Each eductor line, 460 meters long, contained 215 eductors each. That is a drawdown point every 2 meters. That was our design. this is what happened. The groundwater level, 3 meters below the surface. The wells and eductors here produce a drawdown curve like this. Around-the-clock pumping enabled the boot pit to be constructed in the dry and consolidation of the lower clays. Consolidation of the clay occurs because of the pore water pressure reduction. This reduction increases the effective overburden pressure of the sand, preloading the clay in advance of the construction. The dewatering reduced the water pressure here above the clay, but of course the pressure still remains below. So sand drains were installed through the clay to relieve this pressure. Measurements undertaken during construction indicate that a consolidation of 35 millimeters occurred in the 3 meter thick clay layer.
The first stage in the dewatering is the installation of an outer ring of 30 deep well turbines to penetrate the clay layer to a depth of 28 meters. A temporary casing, 305 millimeters in diameter, is installed rapidly to the clay layer by means of an internal high-pressure water jet. Penetration into the clay layer is achieved using the internal jetting pipe as a driving tool. The jetting pipe is withdrawn, and the permanent PVC well casing, 150 millimeters in diameter and 29 meters long, is installed. The well casing is slotted over the bottom 6 meters to act as a screen. A filter of crushed stone is then placed around the screen. The jetting tool is used to hold down the permanent well casing as the temporary outer shell is withdrawn. The wells, fitted with hydraulically operated turbine pumps having a capacity of 12,000 litres per minute, connect with the main dewatering lines. Eductors are also installed by jetting a temporary steel casing into the clay layer. First, the 50 millimeter diameter PVC outer casing of the eductor fitted with a bottom screen is lowered into the hole. Coarse stone filter is placed around the screen and the hole backfilled. The eductors work on a vacuum principle through a venturi fitted to the lower end of a 25 millimeter internal PVC pipe. The complete assembly is placed inside the outer casing so that the venturi is located just above the screen. Each eductor is capped and connections made to the main supply and discharge lines. The eductors operate through the introduction of feed water at 860 kilopascals into the annular space between the inner and outer casings. This water is reflected upwards through the venturi into the inner pipe. This creates a vacuum at the venturi which sucks the groundwater through the screen into the eductor. Groundwater won from the adductors is fed into the discharge header lines with a flow boosted by large vacuum pumps. 7 main pumping stations provide both the high-pressure feed water for the adductors and the booster discharge system. The commissioning and subsequent operation of the dewatering system requires constant monitoring and tuning of each adductor in order to maintain the optimum adductor output of 50 litres per minute. Inherent in work below ground is the unforeseen. Bands of cemented limestone and solution cavities seriously affect the drawdown rate. To meet the schedule, almost 1,000 adductors are installed, totally encircling the site, more than double the original requirement. Abrasive elements in the groundwater cause rapid wear to venturi components. In some areas, replacement is necessary as many as 25 times. These problems and many more are overcome. The groundwater is under control. Piezometers are used to monitor the drawdown. A tape bearing an open electric circuit is lowered into the piezometer. Contact with the groundwater completes the circuit and indicates an accurate water level. Deep settlement gauges are leveled periodically to record consolidation taking place in the clay. With groundwater under control, construction of underground work to 16 meters below surface can proceed in the dry. Predictably, with the dewatering works of such magnitude, the effects are not confined to the site alone, much to the consternation of the neighborhood. On the nearby housing estate, the shallow wells used to water the gardens run dry. Water won on site is pumped back into the ground to form a natural barrier across the end of the estate. Supplemented by a little help from the water board, the grass was never greener. But the residents of the adjacent caravan park sleep is the problem. The noise level of pump stations on round-the-clock operation is reduced to an acceptable level by the construction of baffle walls and modifications to the exhaust systems. Peace and quiet returns. Of the 27 million litres of water won from the ground each day, 5 million litres is used in the densification work. 4 million litres is continuously recycled to operate the adductors. 1 million litres is used for dust control purposes, and the surplus of approximately 21 million litres is discharged into the sea.
Just 150 metres from the site, the Indian Ocean and the shores of Coburn Sound. It is the sea, in its comparatively recent retreat, that has left behind the unstable sands, which must now be compacted if they're to safely support this huge complex. The task, to compact the sand in situ beneath the structure to a depth of 23 metres. The solution, to move 1.5 million tonnes of sand grain by grain. The method, the Franke-Keller deep vibro compaction process.
Vibrocompaction. Its success, the key to satisfactory performance of the whole foundation. Its achievement, requiring the mobilization and operation of $1.5 million worth of special plant and equipment. The development of techniques to suit the subsoil conditions, and the risk and challenge of applying vibratory compaction principles on a scale never before attempted. 10 vibrocompaction machines are used, 8 on the vertical silo complex and 2 on the horizontal storage facility. The vibrocompactor units are developed especially to permit vibration and compaction at great depth. The area to be treated extends 13 meters outside the raft. 12,000 vibro probes are to be installed at 2.13 metre centres on a triangular grid to provide uniform densification of the variable kwinana sands. Careful planning is required to ensure staged completion of each area so that construction can follow close behind. The vibrator consists of a tubular steel casing, diameter 25 centimetres and length 5 metres. An electric motor is used for the upper portion of the vibrator and provides the rotary power necessary to drive a series of eccentric weights located in the lower portion of the unit. The revolving eccentric weights induce oscillations in the vibrator casing, which set up vibrations in the surrounding soil. The vibrator unit is fitted with follower tubes to give an overall probe length of 25 metres. The vibrator itself is isolated by a rubber coupling. The complete vibro probe, weighing 8 tons, is suspended from a 55-ton crawler rig that has the capacity to meet the heavy extraction forces. Individual vibro probes are installed in the following manner. High-pressure water is fed to the toe of the vibrator through the follower tubes and pipes on the outside of the vibrator casing. The motor is switched on, and the probe penetrates into the soil under its own weight. The vibrations cause a temporary liquefaction of the saturated soil surrounding the probe. Penetration continues to a level just above the clay. Electrically driven pumps feed water by pipeline and flexible hose to the top of the probe. Water and electrical controls are mounted on the crawler rig and are operated by the driver. Penetration is accelerated by the introduction of a secondary external water jet. Hard bands of limestone make penetration difficult, affecting verticality and causing breakages and extraction problems. These are minimized through reinforcing of vibrator casings, introduction of coupling strengtheners, addition of fins to break up the limestone, extra high jetting pressures. Probe penetration time averages 20 minutes, during which 70,000 litres of water is consumed. The probe holes are flushed clean of silty, cohesive materials prior to commencing compaction. With penetration complete, the water is turned off and the vibrator allowed to sink to the bottom. Under the action of the induced vibrations, the sand particles surrounding the vibrator are rearranged. With the increasing density of the soil, the vibrations are transmitted over an increasing radius. Continuous uniform compaction is achieved with staged withdrawal of the vibrator. The effects of compaction and settlement taking place in the soil are evident at the surface in the form of a cone-shaped depression. The loss is made up with natural sand backfill. As probing proceeds, the site surface level falls to correspond with the reduction in volume of the compact soil mass. Each probe compacts a column of approximately 125 tons of sand. To build the column, the material immediately below the toe is firstly compacted to form a base. The degree of compaction is controlled through an ammeter located in the vibrator control box on the crawler rig. The number of amperes is directly proportional to the amount of work being performed underground by the vibrator. Attainment of the required amperage ensures that adequate and uniform compaction has been obtained. Layer by layer, the soil is compacted in lifts of 300 millimeters. Lift intervals marked on the probe allow the rig operators to visually control the movement of the vibrator through each layer. Cones of depression appearing at the surface vary in size with each probe, relative to the looseness of the natural soils in the particular area. Whilst the average compaction cycle is 60 minutes, individual probe times vary widely, being relative to the extent of improvement required. As work progresses, the general site level falls up to 1 metre, a clear indication of the compaction achieved. Extensive quality control procedures ensure that the specified minimum densities are being met. Initially, dynamic standard penetration tests were taken to record the in-situ densities. This type of test in quantity is both time-consuming and expensive. After an initial proving period to allow correlation, it was replaced by the static Dutch cone penetration test. This test measures density by the pressure required to push a 60-degree cone into the sand. To keep pace with the probing, 2 machines operated round the clock. 1,400 tests ensure the quality of the foundation works. The results of a typical post-compaction Dutch cone test are shown here graphically. The consulting engineers called for an average cone resistance of 170 kilograms per square centimetre between depths of 1.5 to 23 metres. The test results show a significant increase in cone resistance when compared with the corresponding test taken prior to compaction. Note the uniformity achieved after vibrocompaction treatment. The tests disclose pore zones of silty material that do not fully respond to the vibrocompaction treatment. In these areas, additional probes were installed to meet the specified density. The exposed site and prevailing winds are tough on both men and machines. Sandstorms from time to time bring the work to a complete halt. High-capacity irrigation sprinklers fed by the dewatering system keep downtime to a minimum. The difficult working conditions and sheer pace of around-the-clock operation required the establishment of a substantial repair and maintenance facility on site. This was equipped to maintain the 17 vibrocompactors needed to keep 10 compaction rigs in full production. Electric power was supplied from a 1,000 kilowatt transformer and controls a facility establishment on site. The daily consumption is sufficient to serve a town of 20,000 people. By no means a minor part of the contract are the foundations to the horizontal storage facility under construction at the same time. This structure, 260 meters long by 76 meters wide, has reinforced concrete retaining walls that also support the roof structure. These walls, together with the underground tunnel systems, are carried on Frankie cast in situ enlarged base piles to 13 meters deep. The adjacent transfer and shipping tunnels are also supported on piles. The soils under the storage areas between the tunnels and the walls are treated by vibrocompaction. A ground-bearing pressure of 150 kilopascals requires compaction to a depth of 10 meters. 3,817 vibro probes were installed at 2.14 meter centers on a triangular grid. The compaction work was carried out with 2 crawler rigs of 33 tons capacity on a round-the-clock operation. The shorter probe depth in this area required a different technique to be used in placing backfill during the compaction process. Prior to compaction, the building area was excavated to the underside of raft and surfaced with a limestone blinding. In order to maintain the site at this level, it was necessary to introduce backfill throughout the construction of the probe. The backfill material was natural sand, won from excavations taking place in the vertical silos area. Penetration tests were taken to ensure that the specified minimum densities were met. 4 Frankie piling machines were used to install 1,468 piles to carry safely working loads of up to 90 tons compression and 60 tons in tension. slab of gravel is placed in the lower end of the piling tube and is compacted with an internal drop hammer. The tube is then driven into the ground by the hammer that imparts a driving energy of 27 ton-meters per blow. The resistance to penetration is measured by the set. The set is the distance the pile tube penetrates into the ground from 10 blows of the hammer falling through 1.2 meters. On achieving a satisfactory resistance, the tube is held by cables to prevent further penetrations, and the plug is dispelled by continuous hammering. Dry concrete is then slowly fed into the tube and forced out into the ground under the hammer until practical refusal is obtained. An average 1,700 ton-meters of energy is used in forming the enlarged base. The reinforcing cage is placed in the tube and concreting of the pile shaft is commenced. Successive charges of low slump concrete are fed into the tube and forced out into the ground under the hammer as the tube is progressively withdrawn. Concreting of the pile shaft is terminated at the design cut-off level up to 4 meters below the surface. As each area is completed, the site is leveled. A sealing layer of crushed limestone is then placed and compacted with a vibratory roller. With surface treatment completed, the foundation's ready to take the extensive reinforced concrete rafts. The horizontal storage facility already receiving grain just 15 months from the installation of the first pile, and the vertical silo complex is well underway. In this time, 21 kilometers of concrete piling and a massive 260 kilometers of vibro probes have been installed. More than 11,000 million liters of water have been won from the ground. And so, for Frankie, a major foundation project has been completed.